You move your hand, you're fighting against a balloon that wants to inflate. And then on top of that, all of our equipment is based on using your hands too. So after 6.5, 7 hours of kind of fighting against this glove, it's a really long day, and your hands are probably the thing that are most exhausted after 7 hours out on an EVA. Well, we're going out to work. You probably saw me move this mini workstation. The way we carry our tools is on a mini workstation, which is carried on the front. Every single tool we use is tethered to us. We do not want to accidentally create satellites. Our primary way of remaining attached to the ISS, if we're not using our hands, are these waist tethers. And you can see they just have a big hook. They go around a rail or anything else on the ISS and latch on, and it actually has a locking mechanism as well to hold us nice and tight. So we always want to have one of these attached if we're not holding on with our hands as well. The back of the EMU has our life support system. The life support system contains all the equipment we need, from a UHF radio down to the oxygen tanks that provide primary oxygen. One of the challenges inside this sealed environment, it's very easy to carry our own oxygen with us, but we generate a lot of carbon dioxide, particularly when we're out there working very hard. So to combat that, to deal with that, we have these canisters called Medox canisters, which are just silver oxide. They are carried in the backpack along with a very large battery, which provides all the electricity for us. I don't have a battery here to show you today because we're in the process of charging them. We're about a month out from doing a spacewalk, and we've already started getting ready for that. So this Medox canister is able to remove about 7 to 8 hours of carbon dioxide that a human can generate inside the spacesuit. EVAs have allowed us to build and maintain the ISS, repair mission-critical hardware, investigate malfunctions, install new hardware, and the view, unbelievable. See you next time. Hi, my name is Ricky Arnold on the International Space Station. We get asked a lot, how do we sleep in space? And it's a great question because we all know how important a good night's sleep is. If you're not getting a good night's sleep, you can count on reduced cognitive function, poorer reaction times, and maybe just being a little grumpy. And up here in space, just like on Earth, those are things we all want to avoid. So, we go around the Earth about every 90 minutes, which means we get 16 sunrises and sunsets a day. So how we sleep is a really good question, because the sun's always getting ready to come up or it's getting ready to set, and we use those cues on Earth to let us know when it's time to begin our day and when it's time to end our day.
Ricky is talking about circadian rhythm. It's the body's natural regulator for sleep and wake cycles based on a 24-hour schedule. Those 16 sunrises and sunsets he mentioned can cause circadian misalignment and sleep deficiencies during long-duration spaceflight. The hazards of lost sleep can range from poor attention at school to on-the-job errors to long-term sleep loss, even chronic disease. Sleep is super important. Hey Ricky, what are you doing on the space station to get some sleep?
Well, here in space, we kind of have to do it artificially. So we have these nice crew quarters. It's about the size of a refrigerator. It's very quiet. The space station can be a little noisy, but it's very quiet in here. And we can control light with a light switch. If we are just middle of the day, we have a light like you're seeing right now, which is just this kind of standard lighting. It's getting close to the end of the evening. You want to dim the light a little bit, kind of for the end of the evening. Or if you're going to be up late and you need to keep awake, we have a really bright light setting. The other thing we have is off. You see how dark it got. Another challenge sleeping on the International Space Station, sleeping in microgravity is really nice because you can just float and stretch out and it's really comfortable. The problem is with the air currents in the International Space Station, you could very well float into a piece of hardware and hit your head, or worse yet, even break something. So we got our sleeping bag here, just almost like a sleeping bag on Earth. But as you can see, we have bungee cords that help hold us up against the wall, so I almost sleep standing up. And also, I do have a pillow. It's just a bag full of clothes, but I actually keep it up on the top of my head because I'm a little tall. In the crew quarters, I tend to hit my head on the ceiling when I'm sleeping. So I got my sleeping bag here. I got my bungee cords to hold me in. And then when it's time to go to bed, it's quite easy. Just unzip the sleeping bag, climb on under the bungee cord, climb into the sleeping bag, make sure you're nice and secure, zip yourself up, plan on getting a good night's sleep, so I have good reaction times, my cognitive ability is what it should be, and that I'm not grumpy in the morning. So with that, I'm all set. Good night from the ISS. Hi, welcome aboard the International Space Station. I'm astronaut Ricky Arnold, and I'm currently at one of our human research facilities on ISS, where you can see centrifuges, laptops, and other scientific equipment. Across from me is another one of these experiment racks, where you can see ultrasound imaging, more laptops, cameras, other equipment, all stuff that requires electrical power. In fact, we have so much equipment for science and life support that our electrical system has about 8 miles or 13 kilometers of wiring to make it all work. So where does this energy come from? Let's have a look. From here in the cupola and through other windows, you can easily see the solar arrays soaking in the sunlight. They are massive. These 4 solar arrays are made of solar cells, which are purified chunks of the element silicon. Together, the solar arrays contain a total of 262,400 solar cells and cover an area of about 27,000 square feet, more than half the area of a football field. That's huge. When the station is in sunlight, the solar arrays produce about 60% more power than we actually need during the daytime. That extra power goes directly to charging our lithium-ion batteries. So those batteries are essential because they provide the power we need during the 16 night times we have per day here on the space station. The energy our solar arrays can produce is enough to power 40 homes, and we can maximize the power we generate by rotating the arrays in 2 axes, one like a windmill to track the sun through the course of the day, the other to track the sun's inclination, or its angle in the sky. The space station's electrical power system uses direct current to provide energy for our laptops, lights, water recovery system, and science experiments. Thanks for coming aboard today. Now back to Earth.
Mission and liftoff. Touchdown confirmed. Hello, United States.
To explore every phase of cosmic history.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between 2 objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground. At least not while getting this much hang time. Alright, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2 myself, applies a force to object 1, then that same force will be applied, according to Newton's third law, by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Welcome to the International Space Station. I'm astronaut Joe Acaba. Today, we're going to talk about potential and kinetic energy. Let's get started. Kinetic energy is the energy an object has because of its motion. An object can store energy based on its position. This is called potential energy. On Earth, imagine dropping an object from a raised position. As an object's altitude above the Earth's surface increases, its gravitational potential energy also increases. The potential energy stored due to its position is now being converted to kinetic energy. We also observe this with elastic potential energy.
Okay, new term. Elastic potential energy occurs when objects are compressed and stretched, or generally deformed in any manner, creating potential energy. Think of this bungee or a spring. Okay, Joe, what's next?
We pull back on the band and create potential energy. When we release the potential energy, it is converted to kinetic energy. Here on the International Space Station, we are still under the influence of gravity, primarily due to our position with the Earth. So, when I have this ball on this ramp, normally back on Earth, I release the ball, and it rolls down the ramp due to a change in its potential energy that's being transferred to kinetic energy. But as you can see, it doesn't happen here. So it doesn't mean we don't have potential energy. It just means we're not converting it at this time to kinetic energy. And why is that? Gravity is pulling us down, but we're moving super fast. And so what it is we're bending around the Earth in this perpetual falling motion. Thanks for joining me on board the International Space Station. We're sending it back to Earth so you can try your own experiment. See you next time.
Hello, and welcome to the International Space Station. My name is Scott Tingle. Here on the space station, we live in a microgravity environment, which makes eating here a very unique experience. To stay healthy, we have to maintain a nutritious diet, just like we would back on Earth. Let's go take a look at some of our food and drinks and check out our meal preparation area. During long-duration spaceflight, we have to make sure that we receive enough energy, proteins, and vitamins. Our food lab back on Earth makes sure we get plenty of each as they carefully prepare, test, and package everything. We combine all of this excellent nutrition with exercise to ensure our bodies stay healthy and strong while we're here. We eat 3 square meals a day just like we do on Earth, and maybe throw in a snack or two. One of my most favorite foods to eat are natural raisins. Here on Space Station, we have to keep our calories up if we want to get all our work done. And the carbohydrates in these raisins really help. And they're kind of fun to eat, too. And how do we stay hydrated in microgravity? With these special pouches. They're filled with water, and we use a straw that has a one-way valve that prevents water from floating out of the pouch while we're not drinking from it. Here's a liquid drink. This is a tropical punch for today. I love drinking fluids on station. Here on station, we have a pretty cool food preparation area. We have a place to get fresh water for us to drink or to put in our rehydratable foods. And we also have an oven to put food in. We pick out some of our favorite foods. Chicken fajita for me. Put it in the oven. Close the door and turn it on. In about 15 minutes, I'm going to have a warm meal. Thanks for exploring a little nutrition with me. I'm going to send you back to Earth so you can create your very own astronaut menus. See you again soon. Hello, my name is Scott Tingle, and I'm living and working on board the International Space Station. You know, I love my views from the cupola. It's our orbiting altitude of around 400 kilometers or 250 miles above the Earth's surface that gives us these unique perspectives. Let's explore how our ISS orbits work. Come on. First, I should explain, orbits are elliptical or oval in shape, with some being almost circular. Planets, comets, and moons have elliptical orbits. Spacecraft orbiting Earth, like the space station, are placed into a nearly circular orbit to keep a consistent altitude as they travel around the planet. Let's take a look at the Earth. It has a radius of 6,378 kilometers, and the station orbits about 400 kilometers above the surface at 8 kilometers per second. That's 17,500 miles per hour. See if you can use these values to calculate how far and how long we travel in one orbit around the Earth. All of this information and more activities related to orbits are available in the accompanying lesson plan at nasa.gov/STEM on station.
Answers coming in. 4, 3, 2, 1.
The answers to the questions, by the way, are approximately 42,600 kilometers and 90 minutes. And due to our altitude on orbit, we have our very unique and awesome view of the Earth. Thanks for exploring with me today. I'm going to send you back to Earth now so you can start your challenge on orbits. See you again soon.
Welcome to the International Space Station. I'm NASA astronaut Ricky Arnold. Our view from the ISS of Earth is absolutely magnificent, but we quickly realized we really should call it Planet Ocean. We are mostly a water planet. Water occurs here in all three phases, solid, liquid, and gas. And the presence of water on other planets and moons within our own solar system has us wondering, is there life there too? Well, why is water so special? One reason is called surface tension. So what is surface tension? Let's have a look. Surface tension is a property of liquids in which molecules of one substance are more attracted to each other than to molecules of another substance. Water is unique in that it has a high surface tension compared to other liquids. This is due to its polar property. The positive hydrogen ends and the negative oxygen ends create a strong bond. As they say, opposites attract. So the hydrogen end of the water tends to stick to the oxygen end in a nearby water molecule. At water's surface, its molecules are only attracted to the water molecules below and to the sides of them, as there is only air above these molecules. So the surface molecules of a body of water are pulled down, creating a more stable, stronger environment. That is why certain animals, like the water strider, can actually walk on the surface of water. Here on the International Space Station, the microgravity environment makes it easy to show how well water uses surface tension to stick together. We even rely on surface tension to help us wash our hair, those of us that have a lot. Thanks for coming along today and learning a little bit about surface tension. Want to learn more about the unique properties of water and do your own experiments? Try out the activity related to this video at the STEMonstrations website. See you next time.
Hi, I'm NASA astronaut Drew Poiston. Welcome to the International Space Station. On our station, our water recovery system is vital to our mission and our survival. Want to know why and how we recycle and filter our water? Let's go. We use water recovery and filtration because it is expensive to launch resupply missions, and the weight of the water is a problem as well. Think about the weight of a single bucket of water. Can you imagine the weight of water for a month's supply for 6 people on the International Space Station? What about the water for a year or more when we leave low Earth orbit for deeper space missions? That's a lot of water, and bringing it with us is not very efficient. On station, we recycle wastewater to get fresh drinking water. This recovery and filtration process includes our urine, moisture we exhale, and sweat, along with the water we use to bathe and shave. It works like this. When we use the bathroom, urine is collected and pumped to a distillation assembly. The assembly spins, pulling the urine to its walls. The urine is heated to evaporate water from the waste and then condensed in the outer chamber to form distillate. Next, the water is pumped to a tank where it is joined with the water recovered from cabin air created by crew sweat and respiration. Down the line from there, odors and any other contaminants are removed with heat. Then iodine is added for microbial control. Our water is checked often to ensure it meets water quality requirements. It is also monitored closely for bacteria, pollutants, and proper pH. The pH scale ranges from 0 to 14 and is a tool used by scientists to measure the strength of an acid or base. Our water is required to be in the 6.0 to 8.5 range. The end result of the entire process is clean drinking water that we get to enjoy every day. The recycled water on the space station is sterile. There's no odor or bad taste. You've seen that water recycling is critical for long-duration missions such as here on the space station and will be for future trips to the Moon or Mars. Be sure to check out the activity connected to this video so you can learn more about water filtration. Thanks for learning with me, and I'll see you next time.
Hey there, my name is Joe Acaba, and I'm living and working on the International Space Station as part of Expedition 53. One of the best parts about living on the space station is being able to float. Just like you walk from place to place throughout your day, we float from place to place throughout our day. However, we have learned that the same thing that allows us to float, microgravity, is hard on our bodies over time. Our muscles and bones are made of millions of tiny units called cells, and these cells can have problems in microgravity. Up here on the station, bones and muscles no longer have to support the weight of our bodies, so they get weaker. Astronauts could develop something called muscle atrophy, where our muscles become weak from lack of use. Each bone in your body is made of cells too. A healthy bone has more density than an unhealthy bone. Weakened bones can lead to a disease called osteoporosis. Fortunately, our scientists at NASA have figured out one way to keep astronauts healthy and strong. It's called exercise. Let's take a look at how astronauts exercise in space. This machine here is the Advanced Resistive Exercise Device, or we call it ARED. It simulates free weight exercises in normal gravity to work all the major muscle groups. ARED's primary goal is to maintain our muscle strength and mass so that we have less of a recovery period when we land back on Earth. Alright, so there's looking at lifting. But what about a little cardio? We have a treadmill for that. Let's check it out. Staying physically active helps both astronauts in space and humans on the ground to stay healthy. And it prevents muscle atrophy and osteoporosis. Now you can try the activity connected to this video to learn more about muscle and bone cells. I'm Joe Acaba, and I hope you enjoyed learning about exercise on the International Space Station. We'll see you next time.
Hello everyone. I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
Alright, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and And we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
On December 17, 1903, two brothers from Dayton, Ohio, would alter human history forever. On that day, Wilbur and Orville Wright flew their wooden and canvas machine off the sandy dunes in Kitty Hawk, North Carolina, becoming the first to flight. Heavy experimentations with gliders, like advancements in engine technologies, controls, and aerodynamics, provided a pathway for heavier-than-air crafts, like the Wright brothers' Flyer. By the 1930s, airships, which have dominated the long-distance flight, were replaced by flying boats and other rudimentary aircraft. By the 1930s and 40s, development of aircraft for war effort greatly accelerated infusion of new technologies into civilian general aviation. This stream of innovation led to the start of the jet age, which would revolutionize both general and military aviation. Later in the 20th century, even more advanced technologies like digital electronics would bring about fly-by-wire, digital engine controls, GPS, and these advancements even changed the way we go about designing aircrafts. This century has been marked by transitioning to large-scale pilotless drones, and for the first time ever, inherently unstable aircrafts, such as highly integrated flying wings, have become a possibility. And with all these advancements in the past 112 years, we're still only scratching the surface of capability and performance, but we're paying a heavy price for lagging innovation. Who here has traveled by air in the past 6 months? Were you surprised by the cost and time of your trip? Today we find ourselves at the doorstep of yet another revolutionary advancement in aviation history: electric or hybrid electric aircrafts. NASA is investing in electrified aircraft propulsion research, or EAP, as part of its portfolio to improve fuel efficiency, emissions, and noise levels in commercial transport aircrafts. EAP uses electric motors to drive some or all of the engines on an aircraft. The energy source for the system can be electric, hybrid, or turboelectric. NASA is working across a range of markets, from urban air mobility to subsonic transport. Each market has differences in vehicle size, range, and speeds. Our strategy at NASA is to work with our industry partners to enable technology development, demonstrate these technologies in flight, and transfer the knowledge to commercial sector for future products and markets. One such emerging market is urban air mobility, developed through NASA's Revolutionary Vertical Lift Technology project. Urban air mobility, or UAM, is a conceptual market that would enable passenger-carrying air transportation in and around metropolitan areas. Think of flying Ubers. These vehicles could use all-electric or hybrid electric propulsion systems capable of vertical takeoff and landing. The overarching goal of NASA's work in this space is to develop and validate tools, technologies, and concepts to overcome key challenges for vertical lift vehicles. A critical challenge for UAM market growth is public's acceptance that these vehicles can be as safe as commercial air travel or automotive transportation. However, the most immediate impact from NASA's work for the flying public is the reduction in cost through fuel burn improvements and lower airfare prices. To put that in context, let's look at some numbers. The overall global fleet of large commercial aircraft totaled over 25,000 in 2017 and is expected to grow to 37,000 aircraft by 2027. Out of the 25,000 aircraft today, nearly 60% of those are narrow-body aircraft, small regional aircraft, both jet and turboprops. Saving just 10% in fuel consumption across this fleet would yield more than 5 billion gallons of fuel savings per year and is forecasted to save approximately 10 billion gallons by 2040. We also have to take into account the reduction into CO2 emissions. So how do we get there? The leading concept that NASA is currently investigating for partially turboelectric configuration is single-aisle turboelectric with IVE Bondrel Air propulsor known as Stark-Able. This configuration is being developed assuming entry into service by 2035. It consists of two underwing turbofans with generators extracting power from turbofan shafts and transmitting it electrically to rear fuselage Bondrel Air ingesting fan. One of the main sources of drag on an aircraft is a layer of slow-moving air that builds up along the fuselage and wings, known as Bondrel Air. Bondrel Air creates extra drag, and we believe we can improve aircraft performance by embedding engines into the airframe and having those engines consume Bondrel Air air. By ingesting Bondrel Air, the drag is significantly decreased, which leads to an overall improvement in aircraft efficiency. Results indicate that this turboelectric concept has an economic fuel burn reduction of 7%, an emission fuel burn reduction of 12% comparing to other aircraft designs. Several years ago, NASA has developed an advanced and highly integrated concept known as N3X, which explored fuel savings by combining a blended wing body design with fully turboelectric and fully distributed propulsion system based on superconducting electric machines and power distribution. The fuel benefits of this configuration is very significant, estimated at nearly 70% reduction comparing to conventional aircrafts such as Boeing 777. This concept has the best benefits so far studied. However, it requires the most aggressive technology and infrastructure development. And last but not least, NASA is building its first ever all-electric X-plane, X-57 Maxwell. This design will demonstrate an effective interaction between the wing, the engine propellers, and the flight mission flight path, while simultaneously solving a number of challenging technical issues for electrified propulsion in crew-rated aircrafts. While electric motors are more efficient than fuel-burning engines, they produce a significant amount of heat during operation, requiring an integrated thermal management system to be incorporated into the design. Now, a common method of solving such heat-related problems is to employ an embedded heatsink or a large metal heatsink or water cooling system. But this can cause a dramatic increase in weight, thus reducing the benefit gained by electric conversion. One such research effort to control the heat generated by these systems was performed late last year by my team, where we developed a 98% efficient 13 kilowatt power system for X-57 high-lift propulsors. Weighing only 2 pounds and completely air-cooled, this system was fully qualified across various facilities at NASA Glenn in 10 short months. And within the next 2 years, our system will be flying on X-57 flights, proving that it is possible to have a lightweight, air-cooled solution for aircrafts. In order to qualify the components in this electrified era in aviation, NASA needed to develop capability to test and verify them before in-flight testing. So we converted our hypersonic test facility in Plum Station in Sandusky to NASA Electrified Aircraft Testbed, NEAT. Currently, this state-of-the-art facility is being used to test full-scale megawatt powertrains with an eye towards incorporating component technologies into an overall system. The facility can support single-aisle aircraft geometries with proper cable lengths and electromagnetic interference mitigation. It can supply power for up to 24 megawatts, thermal management system for up to 2 megawatts, and it even contains an altitude chamber that can simulate up to 120,000 feet. All electric aircraft concepts that we've seen so far rely heavily on advancements of components such as advanced motors, power converters, and material science, to name a few. X-57 work is an example of much larger research portfolio within the field of power systems led by NASA Glenn. Over the past 20 years, Glenn has pioneered designs of various high power, density, and high efficient motors for space, aeronautics, medical, and terrestrial applications. All our work has always pushed the boundaries of what's possible, and our newest motor work is no different. NASA Glenn has a small in-house team that is developing a 1.4 megawatt motor with a performance goal of 16 kilowatts per kilogram and efficiency greater than 98%. The motor contains a self-cooled superconducting rotor, which has never been done before, allowing the motor to achieve exceptional specific power and efficiencies without inheriting external cooling weight penalty commonly attributed to superconducting machines. Integrated rotor superconductor, spinning at 6,800 RPM, 4 times higher than the state-of-the-art, and weighing only 80 kilograms. This motor revolutionizes the field of advanced motors and greatly increased number of aircraft concepts that can utilize hybrid architectures. All our electric motor work is all diverse in size, applications, and power levels. And it's beyond the world of aeronautics. Just 5 years ago, my team designed, built, and delivered a biconical motor to University of Indiana School of Medicine. This motor was designed to help catalyze advancements in the field of cardiovascular assist devices, such as pacemakers for kids who are born with a single heart ventricle. This motor is tiny in comparison to the ones on aircraft, just 2 inches tall, and is powered by a total of 5 watts, same power as USB ports on your computers. Currently, our design is being used to develop a clinical trial version, and hopefully a viable device will enter a market within a decade, saving an estimated 1,500 children per year. All great progress is accompanied with great difficulty and must be enterprised and overcome with answerable courage. In our efforts, we don't underestimate the power of vision and direction. These are irresistible forces able to transform what might appear to be unconquerable obstacles into traversable pathways and expanding opportunities. I am deeply humbled to have an opportunity to be part of this amazing journey, a journey that will surely.
Imagine if you were an alien who, was visiting the Earth for the first time from some other galaxy. Imagine only visiting the United States and never visiting any other part of the Earth's surface. That's essentially what we've done with the Apollo missions. Really been able to do wonderful and groundbreaking science with the samples, collected during the Apollo missions. But again, we visited only a very small part of the lunar surface.
The way that I think about it is it's the equivalent of landing on Earth and getting rocks from Kansas. It would give us insight into one particular location on the Earth, but not at all the diversity of what we see on the Earth, what we know is present on the Earth. So the ability to go to a different site, a different location, get different samples will just enrich what we've already learned from our Apollo samples.
There's a lot left to be learned about the moon, and it starts with the South Pole.
Artemis astronauts will fulfill a different mission in a unique environment. While the Apollo astronauts who visited the moon's surface between 1969 and 1972 landed near the equator, Artemis astronauts will venture to the moon's South Pole region. Frigid, rugged, and with unique light and darkness conditions that make it an ideal location for exploration. The South Pole region is also home to the rim of the moon's largest, oldest, and deepest crater, called South Pole Aitken. It takes up almost a quarter of the moon, and is so deep it exposes portions of the moon's interior.
Yeah, the South Pole it's fascinating. There are some very unique types of rocks that are at the South Pole that will allow us to understand the entire history, not just of the moon, but potentially of the solar system.
Very early on in lunar history, we think that there was this increased period or very intense period of huge material hitting the surface of the moon, creating these really large craters or like giant holes, which we actually call basins.